I figured I'd make a video about denaturing proteins since it involves the drawing of graphs. And it's kind of important. Uh, when a protein or enzymes are a kind of protein that makes reactions happen, when an enzyme or any protein gets denatured, it doesn't work anymore. So it's important to not have them denatured in your body. What is denaturing? It's basically when the protein comes unfolded. So all those hydrogen bonds that we've been talking about that hold the secondary structure together and the tertiary structure to some extent, they get broken. Uh, there's two ways that this happens. Mainly the first way is if it gets too hot, if the temperature gets too high. So what is temperature but a measure of molecular motion? Higher temperature means faster vibration. What literally happens is the protein gets shaken apart when it gets too hot, and those hydrogen bonds come apart. It's important to note that the covalent bonds that hold the amino acids together in their primary structure, those covalent bonds don't break. It's the weaker hydrogen bonds that break first. So let's get down to it. Here's our graph. We're going to graph enzyme activity versus temperature. So enzyme activity, that's basically how well your enzyme is working. And there's going to be an optimal temperature that enzymes have evolved to operate at, and that's going to be probably pretty close to your body temperature, right? Which is 98 degrees. So we can put our peak of our enzyme activity graph at 98 degrees. And if it gets hotter or colder than that, the enzyme isn't going to work quite as well. Now think of any reaction, like an explosion or dynamite. It needs heat to happen. It needs a spark before there's an explosion. So at cold temperatures, pretty much, most reactions aren't going to happen as fast. So just that slowing down of molecular motion will slow down any reaction, including the reactions that enzymes cause to happen faster. So, the reason that enzyme activity decreases at lower temperature is the same reason that any reaction will decrease at lower temperature. But if the temperature gets too hot, there's more vibration, the protein literally gets shaken apart, and it doesn't work as well. The active site on the enzyme that holds the substrate molecule may get misshapen and no longer hold the substrate molecule. And as we get really hot, the enzymes get really denatured and they don't work anymore. I stayed at a cabin one time that had a hot tub, and I set the temperature all the way up because I was like, I really like it hot. Generally, you're supposed to have it between 100 and 104 degrees, and if you check at hotels, they usually have them at about 102. So I had it all the way up to 108 degrees, and I sat in there for more than 15 minutes. And when I got out, I felt a little woozy, and I realized, hey, there's a reason why you're not supposed to sit forever in really hot tubs. One of them is that it gets too hot for your enzymes or some of your proteins, and they will start to shake apart and misfold and get denatured. I might have denatured some of my enzymes. Okay, so the second thing that can cause an enzyme to not work as well is being at the wrong pH, having too much acidity or basicity. And we can draw a similar graph for pH versus enzyme activity. It's still enzyme activity on the y-axis. We just have to change temperature to pH. And just like enzymes have adapted to function well at the temperature of your body, they've also adapted to function well at the pH of your body, which is just over 7. So the peak of enzyme activity for those in your body is probably at just around 7. this enzyme peptidase that breaks down proteins in your stomach. Your stomach has a pH of probably below 2. So it wouldn't really work pretty much all the time if it wasn't, adapted to work at a low pH. So its activity curve might look a bit different. Instead of functioning best at a pH of 7, it might be probably much lower, like 2 to 3, suited for acidic environment. I also want to talk very quickly about how enzymes work. Simply put, we can say that the active site of an enzyme grabs a substrate molecule, and it's kind of like a lock going into a key going into a lock. Here's a picture of that. This is our enzyme. It's a big protein. Here's the active site that's shaped like the substrate molecule that it wants to react. It wants to break apart the substrate. And we can say that the active site pulls apart the two sides of this molecule and helps it break apart completely. But we could also talk about that in a more complicated manner. And for that, I need a graph. So this graph is a graph of energy versus bond length. So think of that reaction we just saw where an enzyme helps the molecule break apart. It's breaking one of the bonds, and that bond is therefore starting short and then getting longer until it's totally broken. So this is the energy of the substrate molecule. Any reaction to get any reaction to happen, you're going to need to add some energy, right? So fires don't just start on their own. You need to have a spark, right? So the energy of the reactants has to go up a little bit. And so as we lengthen the bond, the energy of that molecule is increasing as it becomes more unstable. But then as it starts to really break, the stability increases, energy goes down again until we arrive at the product where the bond is completely broken. Now, with the enzyme helping the reaction happen, it kind of pulls the bond apart a little bit. It lengthens that bond naturally when the substrate molecule is in the active site of the enzyme, and that makes it so that there doesn't have to be as much energy added to lengthen that bond. It stabilizes the transition state, and it lowers that activation energy necessary to get the reaction to happen. The activation energy would be the difference in energy between the reactant and that highest point of our mountain that has to be climbed in order to get the reaction to happen. So when this activation energy is lowered due to the enzyme, the reaction can happen a lot faster. The last thing I want to do is talk about the story of yogurt and how pH and denaturation play a role in it. So let's start at the beginning with milk. Remember that lactose is the sugar in milk. It's a disaccharide. And milk starts at a neutral pH. But as the bacteria eat the lactose, they metabolize the sugar. The sugar gets oxidized. Do you remember what functional group gets made a lot of times when something is oxidized? Carboxylic acid. So the longer the bacteria have to metabolize the sugars like lactose in the milk, the more acidic that milk gets. And now something happens to the proteins in the milk as it gets more acidic. We know that the amino acids on the protein, they have side chains, and some of them have carboxylate groups on those side chains. Now, in acid, that means the fact that the solution is more acidic means that there's more more H plus available. And that will convert carboxylate back into carboxylic acid. Now, here's the important part about all that. Carboxylate has a charge, and the carboxylic acid, COOH, does not. Now, the reason the tertiary structure of a protein can be held together is because of the attraction of carboxylate groups, which are negative, to the amine groups, which are positive. And also, a reason that milk proteins are globular and soluble in water is that they do have charges that interact with the water molecule. So when you remove the charge, you're removing the ability of the protein to form its tertiary structure and to be soluble. So if this protein suddenly isn't soluble anymore, you're going to see it appearing as a solid in your milk, and hence that's what happens when you add something really acidic to milk. Is it'll clump up. What's the word? Curdle. But long story short about yogurt, it's the increased acidity that makes the proteins in the yogurt less soluble and more solid.